Let's explore the behavior of time series models that have roots inside the unit circle. So we'll hop on over here to RStudio in our laboratory here. We will first load up TSWGE, and we will recall that AR1s, if phi1 is less than 1 in absolute, it will produce a stationary time series. But here we have phi1 just bigger than 1 in absolute value. So what will that do? What will be the behavior of this time series realization? So we will first define the phi1, variable phi1 here, to be 1.1. And let's look at the factor table associated with an AR1 with a phi1 of 1.1. And we'll note that this is the factor, of course, that's associated with that model, 1 minus 1.1b, but it will have a root that is inside the unit circle. And again, to rephrase what we had earlier, we'll produce a non-stationary time series if all the roots of the characteristic equation are outside the unit circle. So this one's inside the unit circle, and the absolute reciprocal of that is 1.1, again indicating that the root is inside the unit circle, and it's got a system frequency of 0, which will be associated with wandering, and that is going to be something that we're really going to look at here. Notice that we have the unit circle .wge. That will let us visualize this root. Is the real part is 0.9091, that's this piece, and it has no imaginary piece, and so that's why I've got here the imaginary being 0. That defaulted to be 0, so you wouldn't have to add that in there for just a real, but we've got it in there for completeness. So if we wanted to visualize that root, we could do it just like that, and we see that yes indeed, the root is just inside the unit circle, indicating we have a non-stationary time series being generated here. So this code here, TSWG doesn't have a function that will generate a realization from a non-stationary time series with roots inside the unit circle. So we have to write it ourselves. We've got it right here. The variance of the ATs, the variance of the random noise component, you can set it to be what you want. I've set it to be 1. We're going to generate a realization of size 10, and we'll go up from there. You can go through the initial value here is going to become important to us. We're going to start for right now at 0, and we want the random noise is just that, random. So set seed is going to allow us to generate the same randomness each time. So we can actually see we're going to allow this 10 to become 100 to become 1,000, so that we're generating the same time series and just letting it grow. So let's check it out. Let's see what happens here. Again, remember our phi1 is 1.1. We have roots inside the unit circle. It should generate non-stationary time series. We're only going to look at the very beginning of this realization. Let it run out with 10. And we do it, and this is it. It starts at 0. The random noise happened to take it down first. It could have 50-50 chance of going down or up. And then in the next one, it was 1.1. This value here is 1.1 times this value, plus or minus some random noise. And notice that this is negative, right? It went down first from 0, so it was negative. So 1.1 will be a little bit more negative, but it ended up a little bit higher, so that random noise just happened to be positive. That random draw from a normal distribution just happened to be positive enough to make it a little bit bigger. But then in the next iteration, it was 1.1 times this one, and we got a random noise component that took us down here. But eventually over 10, just the random piece of it, just the random noise was such that you had more positives than negatives, and it eventually brought it up. And at this point, at some point, it kind of reaches a critical mass, and it's really hard for it to turn around again because you keep multiplying it times 1.1. So this is 1.1 times this, so it starts up a little bit higher. It's got a random noise component that was positive in this case. So let's see what happens if I take it out to 20 now. We should still see, because I've set the seed here to be 1, we should still see it go down, up, up. It should look exactly like this. We'll have 10 more observations off the end. So if I do that, oops, if I highlight it first and do that, then there it went. It went down, 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 up. So that's the same 10 that we just looked at, and then it can go up and down, but overall it's going up, which doesn't look too surprising until we let it go out a little bit further, because remember, it's 1.1. That phi1 is 1.1. So if I take it out to 30 and do that, this is the first of the series, but it starts to take off. It starts becoming now 15 times 1.1, plus or minus a little noise. And then 16 times 1.1, plus or minus the same, right? The variance of A is still 1. So you're getting random draws between 2 and -2 each time usually. And so once you get up here, it's hard to really turn that around. So let's take it out now to 100. And if I take it out to 100, boom, it really, so once it becomes big, it's really hard to turn around. It just feeds on itself and takes off. And so this is kind of interesting, right? It's already taken off, but it's only up here to 15,000. When you, even I was kind of looking at this earlier, I was like, that's interesting behavior. If you take it out to 1,000, right? This went up. It's going up exponentially, but once you get out to like 950, right? This is going, these are really increasing. Look, that's 10 to the 40, and that's 10 to the 41. These things just explode up so much so that you don't even see the increase that we saw before. So this is what we mean by explosive behavior. And that's not really, doesn't happen very often, or it's not very practical. It's not a process that occurs in nature very often, so these aren't very useful models in that sense. And if it were, it might be that a mathematical function like e to the x or some other exponential function, deterministic function, might be better at modeling that. So, but just a little bit more on the behavior of this that might be interesting is that the up or downness of this really can depend on the initial value. So notice we said, even once we got back here, right, if we generated that same one, once it starts to, it can randomly bounce around here pretty easy because that random noise component between 2 and -2, usually 95% of the time from a normal distribution, can overcome these, right? It's at -1.5. Well, we can really get that hop if that so happens to be. But once you get up, as we said, once it kind of wanders up into the, beyond 2, 3, 4, 5, it's really hard for it to turn around and really, it can take a couple of moves in this direction, but it's more than likely going to take moves upward. And so it's really hard, once it hits 6 and 7, it's really hard for it to turn around. So what if we started, just to show it, what if we started at, say, 6? And if I did that, we could see, let's just look at that 20 again. If I start at 6, then we can see, even if I change the seed down here, let's change the seed to be 7. So if I do that, we'll see a different one. In fact, let's just take the seed away. And even we're only looking at 20 observations, but now if I take the seed away, it's just going to generate a new one each time. So there's another iteration starting at 6, starting at 6, starting at 6. None of them turn around because it's 1.1 times the previous value. It's going to push it up a little bit and then take the random draw from normal distribution with variance 1. If I increase that variance, then I could have a bigger initial value that would have a better chance of turning around at some point. But you can notice these, like if I change this initial value to -6, right, then it will go down. Those will go down, right? That one's tried to go up, but overall that 1.1, since it was multiplying times a negative number, it pushes it down. Its default is to start by pushing it down, and so overall it's going to make that series explode negative. Again, if we took this to be 100, then it will go and just blow up straight down. Explosive behavior straight down. And again, if we took that out to 1,000, we'd see something similar, that it just, once it hits kind of this other critical mass, the second one, boom, it just takes off big time. So that is what I wanted to show about explosive behavior. And again, that's not usually useful in a modeling sense, where there's more deterministic functions that can be useful if there's something that has this exponential growth or exponential decay. But so primarily from here on, we'll be looking at non-stationary models are super important. It's just, it's usually that the usefulness of them come when the roots are on the unit circle. Less not inside the unit circle when the roots are 1. And we'll explore those from here on. So great job. I'll see you in the next one. Keep up the good work. It's a lot of fun.